Yes, I have 15 televisions, so I'm good to go.
I don't read the top line, but obviously that's fine.
Okay.
Technically, I shouldn't be able to drive, but the doctor said it's not safe if you're going to drive with your mouth having glasses on.
All right, here we go. Okay, we ready? Jake, we ready?
Yeah, I'm ready.
Okay, good.
Let's stay in the back so I'll be by myself. What is the subject matter?
The subject matter is section 4.1. Here's the assignment that I screwed up and didn't put online, but it's there now, so get going on it. Let's look at some of the kinds of questions that we'll see on this. All right, so here's one.
I don't get it. Oh, wow. How'd you do that?
Lots of practice. What was it? Are you kidding me?
Okay, so we want the general solution here to this differential equation. Okay. So all that means is, right, if we're solving a differential equation, our goal, differential equation just means it has derivatives in it. Our goal is to find the function that we could differentiate to get this answer, right? So it's the antiderivative, right? We're just doing calculus Jeopardy stuff here. Now, this looks a little different than some of them we've dealt with. It's got a trig function in it, sure. It's got two terms, but what's our strategy if we have two terms and we're doing antiderivatives?
just one at a time.
One at a time. The same principles that apply for taking derivatives work here, right?
Can you just write the antiderivative formula like up in the corner real quick?
Well, we have a bunch of them.
No, just the one for like general.
For power rule?
Yeah.
Okay, you tell me. What is our formula for power rule? So the antiderivative.
Show me write down the first little bit, and then I'll get the second part.
Okay. You guys finish it. Here's
N
the
minus
standard
1
form.
Of u
Right,
and du equals u to the power of n plus 1 over n.
Okay, I really don't want you to get anybody talking today. I'm dead serious about that.
He's giving you an answer.
Okay, no, I know you are. You go. Go ahead.
Oh, okay.
Yeah, you're good. Equals. No, no cheating. See if you can get it without looking at somebody.
U to the power of n plus 1 divided by n plus 1 plus c.
Good. Okay. Thanks. You remember it for that 10 seconds. That was good. Okay, now remember, and the reason we got that n plus 1 on the bottom is because when we differentiate, we bring that constant down out front. We want to be able to cancel it. Right?
Okay. Yeah.
Okay, because when we differentiate, this is the integrand. That's what we should get back when we differentiate, right? And the c needs to be there because it can be. Differentiating a constant isn't going to show up, so we need to account for that. Okay, so there's one of them. Now we need another one. We need secant squared. What is, now don't look, you don't even need the sheet because you know the derivative, so you can just work backwards. What is our standard form, our antiderivative of secant squared u du? In other words, what do I differentiate to get that?
Tangent u plus c.
Tangent u, there you go.
Plus C.
Tangent u plus c. Okay, so those are the two pieces that we needed, aren't they? Now let's put these into practice here then. So if we're going to solve this thing, what we're doing, y is equal to the antiderivative of all that stuff, right? Times dx. Okay? So this is the stuff that goes in the integrand. It goes between the integral sign and the variable of integration. Okay? That's what goes in there. Now, we've got these two pieces. You already told me what we can do with that. Now, I don't think you're going to want to write this out always, but this time we're going to, because I want you to see the steps very clearly. So we've got this. We've got this first part right here. That one's going to become the, yeah, it's going to be 5x to the 4th dx.
Why can't you do the x to the fifth?
Well, we can. We can, and that's what we're going to do in the future. We're going to do this without having to write this separately, but for now, I'm just going to... and we got this. Okay, so there are my two separate antiderivatives. We don't have to write them separately.
I'm sorry.
Now remember that we can, when we've got constants in there, we can pull the constant out front, right? In this first one, the constant works out great. I mean, it just happens to be just the right constant for us. But pretend it wasn't. Let's go ahead and go through that step of pulling the constant out front. So I've got 5 times the antiderivative of x squared, x to the 4th, sorry, dx minus 4.
X. How do you form? Right?
Just slow down.
Because we want to have the constant out front because it simplifies it. Then it starts to look like one of our standard forms. We never have constants in the standard forms.
Shouldn't that be secant squared x dx?
Yes. Squared x. There you go. Good. Okay, so now what is the answer to this standard form? It's an antiderivative. That's x to the 5th over 5. Good. So this looks like 5 times x to the 5th over 5, and those cancel. Okay?
I just feel like
No, you could have. You're right. What Ethan saw there is it worked out just right at that 5. But what if it had been a 7 or something? Then we would have wanted to have pulled the 7 out front, and when we did the antiderivative, we would have had 7/5 x squared. In this case, they cancel. They won't usually do that. Okay, minus 4, and we already did this, right? The antiderivative of secant squared x dx, you already told me, is just tangent x. Each of those contributes a constant that we'll just lump together into 1,
C sub 2.
right? So then we end up with our final answer is just x to the 5th minus 4 tangent x plus c. Right?
If there is.
Okay.
nice.
That's our calculus Jeopardy game. Okay? So there it is. All right, now, next. Oops.
Oh, yeah?
Yeah.
When we put in the answer, do we put the plus C?
Yes. You have to put plus
He's
c.
a stickler about that.
Yeah, you have to, because if it's a general solution, we don't know the value of c. Now, if it's a particular, if we're given some additional information, then we can solve for it. We'll do one like that too. Okay, so now here's one like that. Here's one like that. This time we're going to find the function satisfying this derivative, right? So we're going to play calculus Jeopardy again. We're going to solve the differential equation, but we're given some initial information this time, or initial condition or particular condition, whatever you want to call it. What does that mean? S of 0 equals 4.
When you plug in 0,
Okay, right here, when t equals 0,
function equals 4.
function equals 4. Okay, so one way to think about that then would be we could even write this as an ordered pair. It goes through the value of the independent variable 0 and the dependent variable 4. So on the xy plane, it would go through that point, right? Now remember, we started to talk about last week, and we kind of ran out of time. We started to talk about how if we look at the solution of the general solution of a differential equation, it's always going to have this constant in there. Sometimes, if it's, as we'll find out relatively soon, if we solve a second order differential equation, so say we start off with a second derivative, and we're going to undo the derivative twice to get back to the function, every process of integrating or anti-differentiating introduces a new constant. And so we're going to end up with two constants sometimes, and then we'll need two conditions in order to pin this thing down. Okay? In this case, there's only one derivative process, and so we had one constant. This family of curves would look like something weird. It would be some group of curves that were just offset vertically. Would be the only difference. That's the family of curves. And a family is a good name because they all are going to share the same characteristics. They won't always be just offset like that, though. Sometimes we'll get different kinds of relationships. We might, for example, we could have a family of curves. Let me just throw one in here real quick. What if we had the family of curves that passed through the origin, for example? Okay, that could be defined as a family of curves, in which case the parameter would just be the slope of the line. They'd all have the same y-intercept. It would be 0, right? And that would just look something like this. In the xy plane, we just have a whole bunch of, right? Each one of those has a different value of m, and that's what distinguishes one from the other. That's what distinguishes the separate trajectories of that family. Now, if we had some particular condition or initial condition, which mean exactly the same thing, let's say that this one had to go through the point 2, 2. Well, then that would be the winner. That would be the trajectory that satisfied that condition, and so that would have been the one that was the particular solution. But in general, we'll solve a problem like this later on in the year, and we'll get an answer like this. We'll get the answer y equals mx, or kx, whatever you want to call it, and that's going to be the parameter.
So we're mostly going to be solving it not for specific, going through specific.
Well, it'll be about 50-50. I mean, it's, yeah. Okay, so now what about this one? So we want to, if we want to solve for s, then. So we want to solve for s of t. Well, s of t is going to be the antiderivative of this function, right? We've got to anti-differentiate both sides to undo the derivative. Right? Now I want you to notice here, there's a lot of stuff that kind of comes together and is consistent. The variable of differentiation is dt. So technically, if we wanted to solve this like algebraically, let's take a quick look at this. And you won't always have to do it this way, but I want you to just see how it works. If I took this differential equation, ds dt equals -3 plus cosine t, if I really wanted to go through the algebraic steps of reversing this thing and solving the differential equation, yes?
Plus 5.
Yeah, 5.
Yeah.
Oh, 5 was. I just get so excited, I probably lose track. Okay, this is what we call, technically, this is a separable differential equation. Those are the kinds we're mostly going to focus on because they're easier. Later on in college, when you study higher level calculus, you're going to spend some time with differential equations. I spent a whole year doing nothing but, after my whole calculus sequence, I spent a year doing ordinary differential equations and partial differential
If you
equations.
get that far.
And, well, I'm just going to assume that you are going to get that far.
I'm not.
You should.
I'm not even going to college.
Okay, all right.
McDonald's manager for Illinois.
And you'll spend like a year, or sometimes, I mean, that was actually a pretty quick path through, it was a pretty intense path through differential equations. If you do a full treatment, it could take 2 to 3 years to go through. I mean, there's a lot of stuff there, and what it all has to do with.
Yeah, no.
No, but I'll tell you what, but actually, when you get to that stuff, that's when the questions get to be really pretty cool, because you can do things like when you're trying to model, just as an example, you could use differential equations to model the vibration of a guitar string, for example, and then you'd know like the end conditions would be if you looked at the guitar. I'm just going to take a second and describe this, and then I'll get back to business. But if you took a guitar string, there's the bridge, and here's the neck of the guitar, right? Then the string gets stretched tautly over this bridge, and then it does something like that. Well, you would know some conditions, some physical conditions about that string. You would know that it's not moving, it's not vibrating there and there, for example, right? And so those would be some of the mathematical conditions that you would be able to apply to this differential equation when you want to solve for the motion of that string when it's vibrating. And so really, I mean, these get to be extremely cool problems then. I mean, they're big time problems that are fun to do. I mean, you can look at wave motion, you can look at all kinds of things. And ultimately, you can look at some pretty weird stuff, quantum mechanics. You can look at the evolution of the Schrodinger wave equation and predict how a system's going to evolve with time. You know, what the probabilistic odds are of particles going to be here or there.
Yeah.
And so, there's some really. This is the basis for essentially all cool math is differential equations. Anything you can do that's really interesting comes from this stuff. Okay. So what do we? So what do we do with this then? This is a separable differential equation. If we want to go through the algebra steps required to solve this, we want to separate the two variables. Notice we've got s's and t's. Well, wouldn't you agree that if I multiply both sides through by dt, then I get this algebraic cancellation, right? And what's really interesting here, I mean, it's predictable and it's not unexpected, but I think it's just really cool that the algebra that we know and love applies to calculus as well. Even though we're dealing with these things like differentials, algebraic cancellation is still algebraic cancellation. You can follow the same old rules of algebra, and you can do all this manipulation of these differential equations, and it works just like you'd expect. So when I multiply both sides through by dt, I get ds equals the quantity -3 plus 5 cosine t dt, right? And now if I want to solve for s, which is my goal, I'm trying to find out what is the function f of, or s of t, right? Then how do I reverse differentiating? What's it? Yeah, I integrate or anti-differentiate. So I'll just do this to both sides, right? And that's how I get my s by itself, right? So what does it end up looking like then? Well, we end up with...
What is that symbol? What is that?
Well, that's called an integration symbol. What it is a lowercase sigma. Do you remember? Well, we haven't really dealt with sigma yet. We're going to. Sigma, an uppercase sigma in math. Well, remember from last year in pre-calc, we did a lot of sigma stuff, right? That's an uppercase sigma. Now that's what we describe as a discrete sum. Matt, you want to hear this? That's a discrete sum. Discrete sum means, well, I really want you to get this. Is an important connection.
That's on the Excel.
It is. A discrete sum means you're adding up pieces of something. You're adding up individual pieces, right? So I'm adding up, and we did stuff like this. We might have said, what's the sum of I as I goes from 1 to 10? Well, that's just 1 plus 2 plus up to 10, right? And we get an answer for that. That's a discrete sum. So we're adding, separate, discrete things. Now, what this does instead, which we haven't learned yet, this is what we're going to start to get into really soon in section 4.2. We're going to start to talk about how we can use this process of anti-differentiation for something completely unexpected.
What?
We're going to use it to add up a continuous sum. We're going to add up a sum of pieces that are infinitely small, which is essentially the same thing as adding up like a fluid. I mean, you're adding up. You can add up a continuously varying quantity. It doesn't have to be, pieces of some stuff that just get added up a finite number of times. It's going to get added an infinite number of times, but the pieces that are getting added are infinitely small, and so you end up with a finite answer. Now that's going to sound a little confusing right now, but it won't soon. And what we usually use that for is to add up the area under a curve. That's mostly what this integration is all about, is adding up areas under curves. If you add up areas under curves in 2 dimensions, then you could add up areas under surfaces in higher dimensions. You could add up areas under hypersurfaces in many, many dimensions. You can do all kinds of weird things with that. But that's what it's for. It's a summative process where you're adding stuff up.
How many dimensions are there?
Well, according to string theory, they'd say there are 11 dimensions, 10 spatial dimensions and 1 temporal dimension in our universe. But we'll get into that later. Okay, so
That's next chapter.
yeah.
String theory.
When you had a job, your cool job when you came out of college, when you were a teacher,
Mhm.
did you use any of this stuff?
Well, I use this stuff a ton. Yeah, use it a lot. So S of t then is going to equal this, right? That's what we got. It's the antiderivative of -3 plus 5 cosine t dt, and now we can just shift into calculus mode. We can just we just play calculus Jeopardy. Yes, sir? That's right. We go into that mode. So now this time let's not split it. Let's not write it as 2 separate parts. We'll just treat it separately. See if you can do this now a little bit in your head. What's the antiderivative of -3 dt? In other words, what would I differentiate to get -3?
-3x.
-3t, right? Because our variable is a t. But we'd have a -3t to within a constant, right? But we're going to glom all our constants together in the end. What about 5 cosine
Plus
t?
5 sine t.
Okay, yeah, the derivative of sine is cosine, right?
Yep.
Does that make sense? Okay, so therefore, the antiderivative of cosine must be sine. So we've got this plus 5
Oh, I know.
sine t,
It's doing the work.
right? And we have the standard forms, but it's almost as easy just to reverse the differentiation process. And then we got to add our plus c.
Just
Okay.
a formality.
So there's s of t. But this time, we're not looking for a general solution. We're looking for
Back down.
a particular solution, right? So we want to use the point that we're given, which is 0, 4. Wasn't it 0, 4?
Yeah.
Yeah. When t is 0, s is 4, right? And see what we get. So this becomes 4.
I asked you. I said no.
Right? So when we plug in the initial conditions, or the particular
Ow.
conditions,
You sack of crap.
Don't
That
say
hurts.
that.
You stabbed me in the head with a
I didn't.
Children.
okay, we've said here. So then we can numerically solve for c, right? So negative 3 times 0 goes to 0, right? What's the sign of 0?
70.
Oh,
Five.
One.
Sign of 0 is what?
One.
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 It's either 1 or 0.
Zero. That's one of the two.
Well, there's 0 is sign the x and the y value.
It's the
Sign is
Y.
Y
Y
value.
it's the
value.
y value.
So what's the y coordinate at that point?
Zero. It's zero. It says
Okay, so then I get 4 equals 0 plus 0 plus c. What is c?
4.
C equals 4.
Ah.
So now that I know the value of c, I can plug that in right there and I get my exact solution, my particular solution. Okay? Make sense?
Yep.
All right.
I thought we could just go to the lab. These seem pretty easy.
Well, they're not too bad.
Why don't we just go to the lab then?
Well, let's just take a peek through here and see what else we
How
got.
about we look and see if there's nothing?
Raise the post.
Okay, no big deal. That one we can do.
But yeah, if they're all like this, then we should have no problem. That one looks.
Okay, and then we get some out of the Larson book, I guess.
You just try this one 3 times.
Okay. Okay, we did one like that. I just want to ask you a quick question on this.
What? What?
Shh. What do we do with this? If I've got one like this where I've got radicals in there, how do I set this up to be able to anti-differentiate?
Separate them, right?
Okay, I'd separate them. What do I do with the square roots?
1/2.
Make them 1/2. So what about the one on the bottom?
Negative.
A negative 1/2, right? No big deal. And then we just apply the power rule. It'll still work.
Simple.
No big deal. Okay, what's that fraction going to become? 4th root of x cubed.
3x to 3.
3/4, good. Yeah. 3/4 power. Okay, no big deal. You can do that. That's not a problem.
Ow.
Okay, now what about that?
Prankster.
What about that?
Just
Outdoor. It says.
Okay, now what about this? That is certainly not one of our standard forms. We don't have an antiderivative. Yeah, we'd have to expand this, wouldn't we? Now that's consistent with what we've done in the past too. If we had a big convoluted product of polynomials that we were differentiating, we wouldn't want to drag ourselves through quotient rules and product rules and all that stuff. We'd rather just simplify it and then make it a polynomial. Polynomials are the easiest functions to deal with. So we would just expand this out and then integrate or anti-differentiate term by term. Okay? Okay, same kind. We just did one like that. No big deal. What we got here?
Uh-oh.
Okay. Now those are thetas. But don't let thetas wig you up. Thetas are just variables. Just variables, right? Could have been an x. Okay, what would we do there? We'd have to distribute. Yeah, good. And then those would look like functions that we could anti-differentiate. Okay, what about this? Something like this. That looks like a mess. Now, we have no hope unless we can...
The 1 minus...
what is 1 minus sine squared?
Cosine.
Cosine squared.
Got it.
Oh, wow.
Okay, so...
You're welcome.
That is a trigonometry.
But I forget those. I didn't.
Okay, now what do we do with that? The sine x over the cosine
Can
squared.
we anti-drive that?
Well, that one
integrate.
we can't. Yeah. Now you guys will be able to do this in the fairly near future. We'll be able to use what's called a U substitution to solve this, but we don't have that yet. Now we can only do the really easy ones that we can somehow make
We're
look.
stupid.
That's your supplier. You gotta use the other side.
Say it again.
So put you in there.
U substitution. That's coming up.
Yeah, why don't we do it now?
Tan X.
U substitution. Okay, you do.
Okay, there we go. So we got sine over cosine. We can split this. Sine over cosine is tangent, right? And then that would leave us with a 1 over cosine, which is a secant. So that looks a little better. If I write this as secant x, tangent x, dx, that's an integrand that we can play calculus Jeopardy with. The derivative of what is that? Secant x, yeah. So our answer would just be secant x plus c, right?
Yep.
Secant x. Okay. Oops, gosh.
I
How
don't
am
really
I going
like,
to do that?
I don't really like how you
I
are.
don't know what you're
Calculus Jeopardy, because it's like you think you're getting away with it.
I think you're playing something fun. Okay, that's one we just did. That's like one we just did. That's okay. I think we're good. I want to just make sure. Oh,
Oh,
Oh.
I'm gonna do it.
oh. Okay, we got to do.
oh wow, that is.
Okay, we got to do one like this.
So we have to do 2 of those.
Yeah.
That's it.
Yeah. In fact, what I'm going to do for you is. Do we have time?
Do you want
Oh yeah, we do.
No, we got
Okay, I am going to. I'm going to run you through. This is. I've been waiting to do this. I love this. We're gonna solve the equations of kinematics, and this is pretty interesting how we can do this. Yes, the equations of kinematics. If we want to know kinematics in physics, just describes motion, right?
I mean velocity, no, or not, minus velocity initial.
Right. So what we like to be able to do. The kinematic quantities are position, velocity, and acceleration, and they're all functions of the parameter time. Right. That's what we want to be able to do. We want to be able to. If we have the equations of motion of an object, we can always predict where its position is going to be, what its velocity is going to be, and what its acceleration is going to be as a function of time.
Mm-hmm.
And then if you go one step beyond acceleration, it's the jerk, right?
Which is what we're dealing with in this problem.
Okay. Okay. All right. So here's all you need to do this. Now, we could derive these from observation in this very classroom. All we'd have to do is we'd have to be able to estimate the relatively constant, I mean, for all intents and purposes, the constant acceleration of gravity is what we'd have to find. That's hard to do, but we could do it. We could roll things down planes, for example, to slow them down, and we could, or we could even, if we had like a strobe light, we could even take pictures of something as it falls, and we could come up with a pretty good estimate of what the acceleration of gravity is. Okay? So if we knew that g was roughly equal to negative 9.8
One.
meters, but we'll only take it to 2 places, let's say. Now we could do that. If we could get this, for sure we could get it to within a tenth of a meter per second squared, no problem. So if we had good equipment, which we do, we go across the hall. So if we knew this, now what we got to remember here is that this is acceleration right now. Acceleration is defined. Acceleration as a function of time is defined as the derivative of velocity with respect to time. Okay? Right? So if I want to solve for v here, I could multiply both sides by dt and get v of t equals a of t dt. right?
Yeah.
Okay? Everybody with me?
Mhm.
Okay, so that's just coming from the fact the
Simple physics. Right?
and this isn't something we're measuring, this is just the definition. The kinematic definition of acceleration is the rate of change of velocity. Okay, so it's the derivative of velocity. Now, if we anti-differentiate both sides then, that tells us that v of t is going to be the antiderivative of this. Well, a of t is just g, it's a constant, right? So we're taking the antiderivative of g dt. Okay, well, what do we do with a constant when we're anti-differentiating? Just pull it out front, right? Or, if we want to, we could even just say the derivative of what with respect to t is g. What would the derivative, let me put it in there like a number and an x, for example. The derivative of what is 2?
2x.
2x, right? So the derivative of what in this case is g. Instead of an x, we got a t in there, but gt, where g is just our constant.
Grand tour.
What year? DT? Must be DT what year?
Grand tour.
That's
Okay.
Lane.
Okay, so gt plus some constant, we'll call it c1. Okay? Now this is the part that's kind of interesting. We want to be able to attach some significance to that constant, right? So let's do this. Let's say whatever the speed of the object was that we're studying, when we start the stopwatch, that's its initial velocity. And that's something that we could specify. It's something that's going to change the outcome, isn't it? Depending how fast it's going when we start the stopwatch. Well, let's just plug in 0. What if we let t go to 0? We'll let t equal 0, and we get v of 0 equals g times 0 plus c1. Well, what's g times 0? 0. Anything times 0 is 0. So that
is
term-
a true fact.
That term is going to 0. And then that tells us what's the meaning of that constant.
Well, for v,
It's
0.
what describe that velocity though? What is that? Starting velocity or initial velocity. There you go. So we'll say that c1 equals, in physics we just call it v naught. It's just the initial velocity. The sub-zero means at the beginning. Okay. So there's our first constant that we've solved for. But we're not all the way there. We got velocity. We got a good equation for velocity. Now we know that v of t equals gt plus v naught. There's one of your kinematic equations, right? But what about position? If we want to get position, well, position, velocity equals the derivative of position with respect to time, right? So we know that v of t equals ds dt, where s is position, let's say. Okay. So if I multiply both sides by dt, I get ds equals v of t dt, right? Okay, well, we know what v of t is. It's right there. It's gt plus v naught. So we end up then with ds equals the quantity gt plus v naught, initial velocity, times t.
Your hair is getting long.
I know, it's ridiculous.
Let it grow.
Yeah, I want to see if you go.
No, I don't think.
How come you didn't go to farm
Okay.
show that off?
What's that?
How come you didn't go to farm show that hair off?
Yeah. Okay, so then if I anti-differentiate both sides, s of t just equals the antiderivative of gt plus v naught dt. I meant to have a ds was v d there. Yeah. Right? Okay. Everybody buy it? We can do this one. This is no big deal. If we solve this, what's the antiderivative of g t to the 1? I can pull the g out front. What's the antiderivative of t to the 1?
Oh, where do you get T?
We got to use the power rule. T squared over 2, right? So the first term is going to give me 1/2 g t squared, right?
Yeah.
And I could have done this for just acceleration. It didn't have to be gravity. It could have been just, these are just the kinematic equations for any kind of acceleration. That would just be an A if this was a constant acceleration. It wouldn't be
Technically,
G.
it is acceleration.
It is. I mean, we pinned it down to be gravity. I could have just said, for constant acceleration, what are the equations of motion? Well, that just would have been an A instead of a G. Okay. And then what about V naught? What's the antiderivative of V naught, which is a constant? dt. V naught t. Plus, call it C2. Okay. We'll do the same trick as last time. If we let's explore what happens when we let t equals 0. So that's going to give us S of 0 is just, we can call it S naught, right? Equals 1/2 g times 0 squared plus V naught times 0 plus C2. Well, look at this. That term goes away. That term goes away. So what's the meaning of the second constant? S naught. Initial
Speed.
No. Initial position.
Oh, S.
Right. And so we end up then getting the formula S of t equals 1/2 g t squared plus V naught t plus, we just found out that that is initial position. Okay. There's our other equation of motion. Right?
So we could just use that one.
Well, this is the one we really need. If we want to be able, the position's the one we really want. We'll use them both. Okay. All right. Now I defy you to tell me that's not pretty good stuff right there.